talk about multiple linear regression now. I have some, if you would like some treats, please feel free to get some cookies or cake in the front as a little post-fall break / post your first exam treat. So today we're going to talk about multiple linear regression, which actually extends quite naturally from what we've already learned, but there's just a couple of things that sort of are going to change. In particular, the degrees of freedom is really the biggest one that's going to change, as well as our interpretation of the beta coefficients is slightly different in the context of other variables. So we can summarize what we know about simple linear regression with these two mathematical statements. The top is just the relationship between x and y that we're positing using this simple linear regression framework. One thing to note here on the midterm, several folks missed this a little bit. The equation for simple linear regression, if you don't have an error term, then you would put hats on beta 1 and beta 0 and y. If you do have an error term, then you don't need the hats, because this is the error basically accounts for any differences in those in those population level estimates. And so y here, the observed y is going to be exactly equal to the true the beta 0 plus beta 1 times the observed x plus some error. And then once we're starting to estimate this is where we would drop the error term and put these little hats on each of these. Okay, so this is the model that we're fitting. Y here is equal to beta 0 plus beta 1x plus epsilon, or plus our error, where our assumption about this error is defined down here. This little, this equation, or rather this mathematical statement, basically covers 4 of the assumptions that we make in simple linear regression. So this says that the errors are distributed, which implies that they're not deterministic. So this is sort of gets at that randomness assumption. They're distributed as this capital N means normal. So this is saying that the errors are normally distributed. And when you're talking about just normal distributions, there are 2 parameters of the normal distribution, the mean and the standard deviation or the variance. And so what this says is that the errors are normally distributed with a mean of 0 and a standard deviation of sigma epsilon. So the assumption here is that the mean is 0 for these errors, which is one of the main assumptions for simple linear regression, and that the variance or the standard deviation is the same for all of the observed, or for all of the errors here. So that's why there's just this single value here, so it's constant. So this second part comes into that constant variance assumption. The capital N here, normal, that's the assumption that they are normally distributed. The fact that they come from this distribution is the randomness assumption. So that's the 4 assumptions: randomness, normally distributed errors, mean of 0, and constant variance can all be summarized by this statement. And then the 5th assumption that the relationship between x and y is linear, that's basically summarized in the fact that you're using a linear model to relate x and y. And then the final assumption, independence, is it's not totally explicitly written here, but that's also kind of plays into it. And again, that independence and randomness assumption, those are not really testable without outside information. And the rest of them we can sort of try to assess via things like the QQ plots and the residuals versus fits plot. Okay, so this is what we've learned so far. We can summarize most of what we learned with these 2 equations, or these 2 mathematical statements. Not much changes when we move to multiple linear regression, except now instead of just having one predictor or one explanatory variable, x, we now have multiple explanatory variables. And so instead of just having the relationship between y and x described by this linear model, we now are describing the relationship between y and x1, x2, all the way up to xk if you have k variables. And the rest of the assumptions still hold, so we still have this error term, and we're still assuming these errors are normally distributed with a mean of 0 and a constant variance. But now, instead of saying that x and y have a linear relationship, we're saying that the relationship between all of these explanatory variables and y is linear. So y here is our response variable, or our outcome variable, and the x's here are our explanatory variables, or our predictors. Okay, how do you think these coefficients, and by coefficients I mean this beta hat 0, beta hat 1, beta hat 2, all the way up to beta hat k, how do you think those coefficients are estimated? What are we minimizing? The error, exactly. It's the same as before. We're still minimizing the sum of squared residuals, or the sum of squared errors. And so this is the same process is going to occur. We'll still, by default, end up with an average residual of 0. So a lot of the same things that you've already done will still be useful. The same, you can still create residuals versus fits plots, as well as those QQ plots for the residuals to check those other assumptions. And so a lot of what we've already learned is going to extend really naturally to this multiple linear regression case. Okay, so I'm going to do an example here in R. I'm going to use this Porsche price data that you've worked with in the past, where the thing we're trying to predict is the price of the Porsche, and I'm trying to use mileage and age to do that. And so just as a reminder, let's just look at what that data set looks like. So let me go to RStudio Pro here. So I can load the stat2 data package, and I can load that Porsche price data set. And we can take a look at that data set to make sure that we know all of our units. So this is a data set that includes the prices for Porsche cars offered for sale at an internet site. So the price is the asking price in thousands, the age is the age of the car in years, and the mileage is previous miles driven in thousands. So we can use those units when we're trying to describe the relationship between these variables. So using what I just told you, what do you think my response variable is, or my outcome variable? Price, yeah, so that's what we're trying to predict. And what are my explanatory variables? Mileage and age, exactly. And so this is how we're going to do this in R. We're still using the LM function, or the linear model function. The explanatory, or rather the response variable, or the outcome variable, is still the thing on the left-hand side of our equation. So we put price here, and we still use that tilde. But now, instead of just having mileage on the right side of the equation, I'm going to have mileage plus age. And so what's different between this and the ones we've previously run is that we've just added another variable. So the way that you add additional variables to your model is just by separating them with this plus sign in the LM function. So we're basically writing out the equation that we think is the relationship between mileage, age, and our explanatory variables, and our outcome variable price. And so this is what we get here as our output. We get our beta 0, 70.9, our beta hat 1, negative 0.5613, and our beta hat 2, negative 0.1302. So in the context of this data, how would you interpret this beta hat 0? Yes.
When mileage and age are 0, the price is 70,000.
Exactly, yeah. So when the mileage on the car and the age of the car are both 0, so basically for a brand new Porsche on this website, the cost is going to be $70,919.20. Right. Now what about, so for this beta hat 1, previously the way we would, how would we have interpreted this if we didn't have age in the model? Yes.
If it was just single regression?
Yes.
It would just be for each increase in, if 1 unit in X, we expect a decrease of 0.56 mileage. Sorry, the other way around.
Yes, the X part was right, but then it'd be a decrease in 0.56 of the price of Y. Yeah. So for every 1,000 miles on the used Porsche, you would expect to see a decrease in price of $561. So that's how you would interpret this if you were just doing simple linear regression. Does anyone know how you would update that interpretation in the context of adjusting for age as well? So basically, this beta coefficient is now interpreted in the context of holding all of the other things that you've adjusted for constant. So what this means is holding age constant. So if you hold age at any constant level, a 1,000 mileage increase on the car will yield an expected decrease in price of $561. So that holding age constant is a necessary piece there now because we've adjusted for it. So that basically means within every age substratum, we would expect that mileage changes the price by this amount, by 0.5613. So using that same definition, how do you think you would interpret age here? Yes.
When you hold the miles as a constant, one unit increase in age will lead to 0.1302 decrease in price.
Yes, exactly. So holding mileage constant, 1 year increase in the age of the car is going to yield a decrease in price of $130 on average, or an expected decrease in price of $130. Yeah. So one thing to just note, two things to note. The first being that when you're talking about any of these beta coefficients, when I'm asking you to interpret them, I always want you to give the units of both x and y. So make sure that you're talking about like the mileage is in terms of 1,000 miles on the car, the age is in terms of years. So when you, instead of just saying a 1 unit increase, describing what that unit is, and similarly describing what the unit for the price is or the outcome as well. The other important piece is making sure that you have some kind of indication in that statement that this is an expected value or an average value. So this isn't like, it's not deterministic. There's some kind of modeling that happened here. And then the third piece is now that we've adjusted for things, we need to make sure we say holding all the things we've adjusted for constant. So a 1 year increase in the age of the car. So there I've mentioned the units there, 1 year increase, yields an expected, so saying that it's expected basically implies that this is like not deterministic, it's from a model, an expected decrease in price of $130, and making sure that we said dollars there, that's the units for the price, holding mileage constant, so making sure we've specified that we're holding this other variable that we've included in our model constant. Yes?
What would the graph of this model look like?
The graph of the model, that's a great question. So let me show you. This is not this data. So actually, you know what, we could look at a graph of this. So let me see. So there's a couple different ways we could do this, but let me show you. We could fit this exact model. So it's going to be the price, and then it'll be mileage plus age. So this is our model that we fit, and we could create a scatter plot. Here, let me just make a little R script. So let's add our predicted values. And this is my little model that I already fit right here. So on the x-axis, So this is where it's a little tricky to know exactly what to plot on the x-axis because now we have two variables, but we could look at it across each of them. So for example, we could look across mileage first on the x-axis, and on the y-axis we could put the price. And then I also could look at a line here where on the x-axis I have mileage and on the y-axis I have y hat to see kind of what that line is going to look like here. And similarly, I could fit and so this is, if you were to draw like the straight line, if we were to predict new values of x, this would be exactly like a straight line there. I could also look at this by age to see kind of, oops, how that, and that looks really funny because these is, hold on, we could change this, we could make a new data set. Let's see, let's go from 0 to 20. And we can make So the way that we would have to do this, we'd have to fix the mileage at a certain value here to be able to actually like get this line that we would expect. So for example, I could set the mileage to anything, and it's always gonna, so let's say I just set it to 1. And so this predicted my y hat values here for each of those, and I could look at what that would be in this new data. And so in my new data, this is sort of a little bit inconsequent, but basically, let's look at a couple different mileages. If I did it at 1, this is what the data would look like. If I did it at 3, for example, my axis here shifted, but the line looks exactly the same. The slope is the same. So what basically this means is regardless of what my mileage is, the slope is staying constant for every change in age. Does that sort of... So another way to visualize this is I could, and I'll show you this in a little bit. This is a little bit of a different example because this is where we have like the additional variable actually changes the relationship that you're seeing. But here's like, if the variable here were some indicator that tells you which group you're in by these different colors, basically the slopes of these lines in theory are the same. So the beta coefficient is the same for that beta 1 value. But you have a different, like each of these groups ends up with a different intercept. So you sort of have a different spot that those lines are starting. Does that kind of? And each of those, the like intercept is just determined by, so within each of these groups, like holding the group constant, that line looks exactly the same, but you have a different spot that they start depending on what group you end up in. All right, that was a good question. Let's see. Okay, so how do we get the predicted values for y hat? Well, this is what I just showed you. It's exactly the same as what we've done before. We just use that fitted function like we had previously where we stick the model object into that fitted function to be able to get those predicted y values. And so now this y hat is dependent on both mileage and age, not just the single x value. So it's dependent on all of the variables that you've put in your model. Yes?
So I have a question about what does the hashtag less than mean in the previous code?
Oh, this right here? This is just a comment. So a hashtag in R just is a comment, and this was just to highlight that this is the line that I was wanting you to look at. Good question. Yeah, so in R, a little hashtag will be a comment, so it will be kind of inconsequential, and here I'm just trying to point to this particular line as being the one where we're fitting the y hat. Yeah, good question. Okay. So the sample size for this data set, let's say it's 30. What would the degrees of freedom for the sum of squared error be now? So before, the degrees of freedom for the sum of squared error when we just had one variable in our model was n minus 2. What do you think it would be in the general case where we have k variables in our model? Yes, n minus k minus 1, exactly. And so for this Porsche price data set, we had 30 is n, and 2, the number of variables. We had mileage and age, and then minus 1. So 30 minus 2 minus 1, or 27 are the degrees of freedom for our errors here, or for our residuals. And so we can see that if we use the ANOVA function, which works exactly like it worked previously, we now are going to have in this table, we've got a line for mileage for this first variable, and this is the sum of squares for that variable. We've got a line for age, and this is the sum of squares for that variable. If we add these two together, that's the total sum of squares for the model. And then we have the sum of squared error, the sum of squared residuals here for the remaining error that's unexplained by the model. And it gives us the degrees of freedom here of 27 for the sum of squared error. Okay, so why might we want to do this? What would be the context in which we'd want to fit a multiple linear regression model? So this is like a little flow chart that comes from this article in Science, or it was generated based on a flow chart there that basically tries to talk about different scenarios that you might find yourself in where you might want to fit a model. And the ones I've highlighted here in green are the main ones that we're going to be interested in. So the first case would be if we were interested in some kind of exploratory analysis, if we were trying to do some kind of inference, or if we were trying to estimate a causal effect. In each of these cases, basically the reason why you would adjust for variables is because you're trying to understand the relationship between x and y, and you think that there are some other factors that might influence that relationship. Oops. And so, So basically the big picture here is that we're trying to do multiple linear regression for inference. And so what do I mean by that? I mean, basically our goal is to discover the relationship between some response in outcome y and some explanatory variable x. And we need to adjust for all known confounders in order to make sure that x and y, the relationship we're seeing, or that beta coefficient we're seeing, is actually the true relationship and not one that's really due to something else. So have people heard the phrase correlation is not causation? Yes, this is a very common phrase. What would be the circumstance under which you would see a correlation, but it wasn't actually causal? What makes that happen? Well, what makes it look like, if you looked at, let's say you saw the relationship between x and y, it looked like the correlation was like 0.5, but really that wasn't a causal relationship. X didn't really cause y. It just looks like they look correlated in your particular data set. What makes that happen? Exactly. There's another variable that is sort of confounding the relationship that you haven't adjusted for. And so this is exactly why you would, in multiple linear regression, you might adjust for additional variables if they are known confounders. And so what that means, basically a confounder, does anyone know the definition of a confounder? Have you heard this term before? Yes, is a confounding variable? Yes. What would make something a confounding variable? Yes.
I think that it puts out an effect on both of the other variables.
Exactly. If it's in the causal pathway for both x and y. So basically, if you have something that could cause your explanatory variable and could cause your outcome variable, then the relationship, if you don't adjust for that, the relationship between x and y could look like there's a relationship there when really it was all due to this third variable. So a confounder is a variable that's associated with both the response variable y and the explanatory variable x, and if not accounted for, it can result in seeing a spurious relationship between x and y. So this is pictorially, sometimes people draw these things called directed acyclic graphs, where basically you're trying to quantify or draw the relationship between different variables. So here, if you had some explanatory variable x and you thought it was related to some outcome y, then you might draw this arrow to say that you think that x causes y. And if you were trying to quantify the relationship between x and y and you thought that the relationship was linear, then you might use a simple linear regression model, and the quantification of that relationship would be that beta hat 1 coefficient, the coefficient that you get for your x variable. And so in the presence, if there were no confounders, then that really would be the true effect of x on y. But if there were some z variable, which in this case is a confounder, the way this is drawn here, you can tell it's a confounder because it causes, so it has an arrow from that variable to x. So this z causes x and z causes y. If this existed, then there might not really be a relationship between x and y. That beta hat 1 that you got from the simple linear regression may not really be the relationship. Once you've adjusted for z, that might actually be 0. So we would like remove the arrow in that case. So a common example that people use when talking about confounding is the relationship between ice cream consumption and crime rates. And so if you collected some data on like the number of ice cream cones consumed over time, and at the same in that same time period collected crime rates, it turns out that if you fit a simple linear regression between these two, you would get like a positive beta coefficient. So it would look like for every one additional ice cream cone consumed in a certain region, crime rates are increasing by beta hat 1 amount. But it turns out there's a confounder here, which is like the time of year. So summer, people consume more ice cream in the summer, and it turns out that summer also is related to increased crime rates, maybe due to people having more time on their hands or feeling energized by the sun. I don't know. I'm not sure why. But this is a relationship that has been described. And once you adjust for summer, then you would no longer see the relationship between ice cream consumption and crime rates. And so in the context of multiple linear regression, what that means is if you had a regression model where the outcome was crime rates, and you have one of your x variables is ice cream consumption and the other is summer, once you include summer in your model, your beta hat 1, the beta hat between ice cream consumption and crime rates, would go to 0, and your summer coefficient would basically explain all of that variability that you previously were explaining with ice cream consumption before you had added this variable. So one of the main reasons people fit multiple linear regression models is if they're interested in the relationship between some variable and some outcome, and they want to make sure that that relationship they're seeing is really due to that variable itself and not due to some other factors. And so you might adjust for those other factors to get that correct. Another common example, this is from my area of research, so most of my research is in the medical field, and a really common example of confounding that people talk about a lot was back in the 80s and early 90s. A lot of women were using hormone replacement therapy. Older women were using hormone replacement therapy like as they were aging, and people were interested in whether this was related to heart disease. And so it looked like in observational data, so that's like data where people were not randomized to get hormone replacement therapy or not. They just some people happened to take this and some people didn't. And they looked at this data and they tried to see the relationship between this hormone replacement therapy use and heart disease. And so this is a plot here of a couple different summaries of studies that looked at either current, past, ever, or any use of hormone replacement therapy. And all of them looked protective. So this line here is at 1, and points on the left of the line mean that there was a reduction in risk, and point on the right of the line means there was an increased risk. And so these initial studies that were coming out all looked protective, meaning that hormone replacement therapy was actually protecting people against heart disease, which sounds really positive. But it turned out that then they did a randomized study to check whether this was true. And in the randomized study, they found that that effect was no longer seen. And in fact, maybe hormone replacement therapy was a little bit harmful. And what was actually happening here is there was this third variable that wasn't adjusted for, and that was socioeconomic status. And so women who were from higher socioeconomic status, so who came from more means, were more likely to use hormone replacement therapy. This was sort of like and it wasn't like a necessary treatment, but more of an add-on. So you had to have a little bit of money to want to do it. And coming from means also is associated with basically generally good health outcomes, just in general. And so what they were seeing here was this spurious relationship really driven more by socioeconomic status than by this treatment itself. And so this bottom part of the graph is showing even in those observational studies, after they adjusted for socioeconomic status, the protective effect basically goes away, and sometimes you can see the dots were a little bit on the right side of 0, meaning that maybe even this was a harmful drug. So all this is to say that thinking about confounding is really important, and even in like large-scale studies where where like big medical decisions are being made. Sometimes the confounders are not always thought through, and it can actually have like big implications for all different kinds of things. And so this is an example where multiple linear regression, where you're adjusting for other things. In this case, the outcome would have been the risk of heart disease. The explanatory variable, the main one of interest, would be whether or not you were using hormone replacement therapy. And then the additional confounder that you would be adjusting for would be the socioeconomic status here. So just to sort of motivate that this is a worthwhile thing to learn about. Okay, so we're going to do an example in R, but just as a quick aside, so far the data we've been using has been included in an R package. So to access the data, you've been able to use either the data function or you haven't had to run anything at all because it just sort of loads when you load the library. But it's generally good to know how to read any kind of data into R, and so that's what we're going to do today for an example. I'm going to show you how you can read a CSV file into R, and it turns out that an Excel file or other types of files can also be read in using a similar type mechanism. And so we can use this read_CSV function, which it comes from the readr package, but it turns out it loads when you do library tidyverse, and so this will automatically load when you load the tidyverse package. And this function, it's quite simple to use. Basically, you set the name that you would like to call your new data set. So in this case, I'm going to call it DF. And I assign to that object in R the output from this read_CSV function, where in quotation marks, I just put the file path to my CSV file, which if we're using an R project like you use for our application exercises, this can be just a relative path within that project. So you don't need to put the full path name. You can just put kind of relative to the top folder of that project where that file is located. So we're going to use this for this example. And the example we're going to be using is from some administration data from the University of California, Berkeley. So there was a study that was carried out by the graduate division of the University of California, Berkeley, in the 70s. And the goal was to evaluate whether there was a gender bias in graduate admissions. And so the data come from 6 departments. This particular data set, for confidentiality, just calls them A through F. But I think actually the original paper mentions what some of these different departments actually were. And basically this data set, it has information on whether the applicant was male or female and whether they were admitted or rejected. So the overall goal here is to see if there's some kind of disparity in who's getting admitted to graduate school. They wanted to make sure that they weren't maybe admitting kind of percentage-wise more men than women or vice versa. And so first, we're going to evaluate the percentage of males admitted, whether it is indeed higher than females overall. And then we're going to calculate the same percentage for each department. So the context here is that our outcome is whether you are admitted or rejected to the program. The explanatory variable of interest is gender. And then the potential confounder that we're going to look for is department, so which department that you're in. Now, admitted or rejected, this is a binary variable. This is not a quantitative variable, so we're not actually going to fit a model to this because we haven't yet learned how to fit models to data that's not numeric, although we are going to learn that before the end of the semester. So we're just going to sort of visually look at this to be able to see kind of how these are related to each other. So to do that, I want you to copy this template into RStudio Pro. And if you run the first 2 chunks, the first one is going to load the packages, and the second one is going to load that CSV file for you. And then I've written some code that will calculate the proportion of each gender admitted and rejected, so you can just run that code and look at it. And based on that, you can see if you think that that there's a relationship between gender and admission. So is one kind of group being admitted more than the other? And you can create a bar plot with gender on the x-axis filled by the percent admitted, which is going to give you the exact same information as part 2, but sometimes it's a little bit easier to see that visually. And then I want you to amend the code from number 2 to calculate the proportion of each gender admitted and rejected by department. And then finally, update that bar plot to facet by department. So you can look at that percent in each one and sort of try to determine whether you think department might be a confounder here. So whether department might be making it look like there's a relationship where there's not. So I'll give you a couple minutes to work on that, and then we'll do it together. Okay, so what did you see when you looked at just the relationship between gender and the percent admitted or rejected? Yes.
Proportion of males admitted is higher.
The proportion of males admitted is higher. So it looks like maybe there's a disparity such that there's like maybe favoring of one of the groups than the other. And then what happens when you look at it by department? Does that change that relationship? Okay, maybe we'll do 4 and 5 together here. Let me switch over to our studio. All right, so I'm going to open this QMD file, and I will run the packages, and I'm going to load my CSV file. So you'll notice here when I use this read CSV, when you got my template files, I had a folder called data that has this ucbadmit.csv file. You can look at this file, it's just a CSV file. If you would like to add your own data to RStudio Pro to analyze, you can upload it using this little upload button here. And as long as you put it somewhere in this folder that includes this, that has your R project, then you can just reference that with the relative file path. And so instead of having to put like home, application exercise, Apex 13, data, UCB, admit.csv, I'm able to just put data/UCB admit.csv because R knows to look, the top folder it looks in is my project itself. All right. So if I run this first set of code, what does this 0.30 indicate? Yes, so this says that 30% of females that applied were admitted and about 70% were rejected. And you could compare that to 44% admitted of males that were admitted compared to 55% that self-identified as male that were rejected. So just walking through what this code is doing, first I'm taking my data set and I'm counting gender by admission. So this just will count every unique combination of gender and admit, those two variables. It'll count how many fall into every unique category of those. And so I end up with 577 females that were admitted compared to 1,278 that were not. And similarly, I have the same, I count the same way for the males. And then in order to get that proportion, I'm going to group by gender because I would like to have the denominator here be gender. And I'm going to mutate such that I create this proportion, which is just n, which is going to be this value, divided by the sum of n, which is going to be the sum within each of the gender categories since I've grouped by gender. So that gives me that 30% and 70%, 44% and 55%. So this is fine as a table, and it's actually, we get the information we need from this. We can see that it looks like that females are admitted at lower rates compared to men, but it also could be helpful to look at a plot, and it's definitely going to be helpful to look at a plot when we're actually trying to divide this by department since there's so many departments to look at. So that's what we're doing down here. We're using ggplot here to create a bar plot. And so if I wanted to create the bar plot that has gender on the x-axis and fills by whether or not they were admitted, what would I put for this first argument? Gender. And what about for the second one? Admit, yep. And so I see basically that same, gives us kind of a repeat of the same information we saw with the numerically where we can see here in red, there's a smaller proportion of females admitted compared to males. Okay, so now we want to update that code to calculate the proportion of each gender that's admitted and rejected to UCB by department. So now, instead of just looking at that overall, we're going to split this out by department. So what do you think I'm going to put for this count function? Department, yes. I'll put department, and then what would go in the next argument? Gender. And then admit, yeah. And so if I just run these top two lines, it's going to, for every unique combination of department, gender, and admission status, it's going to calculate n, the total number that fall into each of those categories. And then if I would like to now summarize this with a proportion to look at the proportion within each department of each gender that gets admitted, what do you think I'm going to group by? Yeah, I'm going to group by department and gender here. So now I end up with these proportions. And now we can look at this first one to give us a sense of what's going on, but there are a lot to look at here. You've got basically, we'd have to scroll through 3 pages of output in order to see all of the different proportions. And so instead of trying to make sense of this big table, let's just plot it. It's a little bit easier to see kind of what's going on once we've split by department. So to do that, I'm going to copy this same code, but now we're going to facet by department. Okay, if I would like to recreate this plot, but faceted by department, so basically creating the same plot, but within each department, what would I do to change this? So I could, if I change x equals to department, I could do that. But what that's going to do is it'll show me the percent that are admitted or rejected within each department, but it doesn't give me a sense of gender. And so what I'm actually trying to do is I want the plot to still have gender on the x-axis, but I want to facet it such that it's creating a separate plot for each of my departments. The code's going to be, do you remember back when we did lab 1 when you created those like multiple plots for each of the different data sets? What function did you use to be able to facet by those? Anybody remember? It turns out RStudio has a nice autocomplete. So if we start writing the word facet, it'll actually autocomplete and let us know what we need here. And so since we want to facet, we could use actually any of the facet wrap or facet grid, but we can use facet wrap here. And so we're going to facet it by department, which will create a separate one of these plots for each of the departments. And so now let's just look at department A. What does it look like is going on in department A? Yeah, a higher proportion of females are admitted compared to males. And if you look at the remainder of them, what does it look like? It looks more even. So in the one department where it looks different, it actually looks like females have an advantage. And in the remainder of the departments, it looks pretty even. And so basically our conclusions, once we've adjusted for department, flip. So rather than seeing that males are admitted at higher rates, it looks like actually if we adjust for department that there's pretty equal admission between men and women, except for one department where actually more women are being admitted than men. So how is it possible that when we looked at it on average across all the departments, we saw that it looked like there was an advantage for men to be admitted, but then when we broke it out by this particular variable, it looks like in almost all cases it's either equal or there's an advantage for women? Yeah, so exactly. Basically what it suggests is that department is a confounder. And so which department you're in is dictating your split of men and women. And also which department you're in is dictating your probability of admission. And so what must be happening here is that there's some department that has a lot more men applying to it that also has basically easier admission versus there's some departments that have a lot more women applying that have less easy admission. And so when you look at the overall average, it looks like there's a disadvantage to being a woman when in fact there's actually maybe a slight advantage. So basically, it turned out what's happening in this particular case is like there were a lot more women applying to harder departments. So I think in this case it was English. a lot, like overall, proportionally, there were a lot more women that applied to the English department, and that department was harder to get admitted to, but it was harder kind of across the board. But because there were so many more women applying to it, it looked like there was a disadvantage to being a woman as opposed to men were applying to easier departments to get admitted to. Like, I think in this case it was engineering, maybe was the easiest one. And so because there were a lot more men that applied to that, it skews it so that when you look at the overall average without accounting for department, you can think that there's an advantage to being a man when in fact it's really just this departmental differences. So here is an example where it's important to account for the confounder in order to get like the right interpretation of the data. Okay, so what was our response variable, our outcome variable in this example? What were we trying to predict? Admission, yeah. And what was our explanatory variable of interest that we were trying to see if it influenced? The gender, exactly. And what was our confounder? Department, exactly. So our equation then is going to be, we're trying to assess the response here, admission, whether that's equal to our explanatory variable gender plus our confounder department. Now, we can't just plug that exact data into a linear regression model because admission here is a binary variable, but we eventually, by the end of class, you'll learn a new modeling way to be able to actually predict when you have binary responses as well. So this is an example of confounding, but it's also, there's the term Simpson's paradox refers to a specific type of confounding that we see in this particular case, where basically the effect looks like it's in one direction when you look on average across the whole data set. So in this case, I've switched it to a linear regression case where we've got y on the y-axis, x on the x-axis. If we look across the whole data set, if we just fit a simple linear regression model with y and x, it would look like the beta coefficient here, beta hat 1, is negative. But it turns out that these particular x's all come from 4 different categories, 4 different groups here defined by the different colors. And if we looked within each of those groups and fit the regression model, we would see that the slopes are actually positive. And so Simpson's paradox refers to the case where the confounder, not only does it change the relationship between x and y, but it actually changes the direction. It totally swaps the direction, which is what happened in the Berkeley data case, where it looked like men were at an advantage when we looked at just the simple case where we only included gender, but once we adjusted for the confounder, the relationship actually flipped to show that females actually may be at a slight advantage in this particular data. The last class had me look up Simpson's paradox to know why it's called Simpson's paradox, and it turns out it was just because it was first described by this guy, Edward Simpson. I think in general, it's just a special case of confounding. So if you understand in general that confounding is when you have some confounder that will change the relationship between x and y, this is just like an extreme example where that confounder, not only does it change the relationship, but it actually flips the sign. So it goes from positive to negative or vice versa. But this term, I think, it comes up enough kind of outside of this class that I wanted to make sure you knew kind of what that refers to, but it's just a case of confounding, which is the more general setting where there's some variable that's going to influence the relationship between x and y such that if you adjust for it, it will change that relationship. Okay, so coming back to the Porsche data, let's talk about how we can calculate some other statistics that we've previously been calculating when we used simple linear regression. So how do you think you would calculate a t statistic for beta hat 2 here? So this beta hat 2 is negative 0.13. How do you think you would calculate a t statistic for this value based on what we did for simple linear regression? Exactly. You take that beta hat 2 and you would just divide it by the standard error. And so we can see what that standard error would be. If we ran the summary function on that model, you would get the standard error for each of those beta coefficients. So for example, the t value for beta hat 2 would be this, negative 0.13 divided by the standard error 0.45, which in this case is negative 0.285. And similarly for beta hat 1, you just take the beta hat 1 value divided by the standard error, and that would get you that t statistic. All right. So it's just going to be equal to the beta hat divided by the standard error, which generally would be just equal to beta hat I divided by the standard error for beta hat I. So this is true no matter how many beta coefficients you have in your model. This would be how you'd calculate the t statistic. What do you think the null and alternative hypotheses are for that t statistic if we were trying to do hypothesis testing and using the p-values that those output? What was the null hypothesis for the t statistic in the context of a simple linear regression model? Yes, so for the t statistic, it was just that the variable itself, like mileage, for example, the beta hat 1 is actually, the true beta 1 is equal to 0 would be the null, and the alternative would be that it's not equal to 0. And so it turns out that that's the same interpretation regardless of how many variables you have. The null is just that that particular beta coefficient is equal to 0. So for example, if we were looking at the t statistic for age, it'd be that beta 2 is equal to 0. And the alternative is just that it's not equal to 0. All right, and if we wanted to calculate a p-value for that, what would be the degrees of freedom for the t distribution that we would use to calculate that p-value? In a simple linear regression case, we were using n-2. What do you think you would use in this multiple regression case? n-3, exactly. So generally, it would be n-k-1. And here k is 2 because we have two variables, mileage and age, so it would be n-3, or 27 in this particular case. All right, so how would you interpret that p-value then? If you get a p-value for beta hat 2, or for that t statistic for beta hat 2, what does that mean? What is that the probability of? Yes.
Value as extreme or more extreme given the null hypothesis is true.
Exactly. It's the probability of seeing a t statistic as extreme or more extreme than the one you've observed given that the null hypothesis is true. So it's the same interpretation as what we had for simple linear regression. It's just for whatever beta coefficient you're doing it for, that you would assume that that beta coefficient is 0. And similarly, for the confidence interval is interpreted the same way here. It's still going to be that if we were to do this process, sample many, many times from the same population and calculate a confidence interval for these beta coefficients using the same tools, we would expect 95% of those intervals to contain the truth. Okay, so how would you actually go about calculating a confidence interval for beta hat I? So in R, we can just use the confint function the same way you would for a simple linear regression model, except now you end up with the number of rows corresponding to the number of variables that are in your model. So in the case where we just had one variable in the model, we just had 2 rows, one for beta hat 0 and one for beta hat 1. In this case, we had 2 variables, so now we have 3 rows, one for beta hat 0, beta hat 1, and beta hat 2. If you were doing this kind of by hand using the output in R, how do you think you would get that confidence interval? Like, for example, how would you get the confidence interval for this beta coefficient for age? Exactly, the beta hat value, so this negative 0.13 plus or minus the standard error here, 0.45 times t star. And how would you get that t star value? be like the critical value from a t distribution with how many degrees of freedom do you think it would have? So it's going to be the same as that degrees of freedom we used to do the p-value. It'd still be n minus k minus 1, so that t star, it'd just be the critical value from a t density with the degrees of freedom equal to the error degrees of freedom in the model. So just, in this case, it'd be n minus 3. So all of those confidence intervals are going to be calculated the same way. The only thing that changes from our simple linear regression model is just the degrees of freedom for that t star value is not going to be different. Okay, so that's when we're trying to do inference, which basically means we're trying to understand the relationship between x and y, which might be that we're doing exploratory analysis, maybe we're trying to draw some inference, or if we really had all of the potential unmeasured confounder, or the potential confounders, we could make some kind of causal claim. The last type of method that you might be trying to do is a predictive model. So that would be like you're trying to predict some value y using some set of x's. So in that case, you'd use multiple linear regression for prediction. And if that's your goal, then basically you're trying to discover the best model for predicting a response variable or an outcome variable using some predictors. And so in this case, ultimately, we're often comparing models. And so we would need kind of some metric to do that by. We're going to talk about a couple different metrics that can help us do that. But today we'll talk about two that we've already learned about and see kind of how they extend in the case of multiple linear regression. So the two that we'll talk about are the f-test and r-squared. And so first, the f-test for multiple linear regression. By default, what this is doing is comparing the full model, so a model with all of your predictors, to an intercept-only model. And so now, previously the null for f-test was just that beta 1 was equal to 0, is same as the t-test. But now that we have multiple coefficients in our model, the null is just that all of those coefficients are equal to 0, meaning that the model that you fit is equal to the intercept-only model. That's the null. And the alternative is that at least one of those coefficients is not equal to 0. So soon we're going to learn a more general version of this that compares nested models. So basically you want some subset of these is equal to 0 as opposed to all of them being equal to 0. But for now, we'll just talk about this one that this is the default that comes out when you use the summary function in R. So the F statistic is just equal to the mean squared model over the mean squared error. What was the degrees of freedom for the model? What is it in the simple linear regression case? It was 1, yeah. And so what do you think it is for the multiple linear regression case? Well, it'd be 2 if you had 2 predictors, but if you had k predictors, it would be k. Yes, exactly. So it's just the number of predictors in your model. And what about the degrees of freedom for the errors or for the residuals? And n minus k, someone said it, I think. What was it? n minus k minus 1. Yeah, exactly. So this is going to be, in the case of the simple linear regression, k was just 1, so this was n minus 2. But in multiple regression, we can generalize it to just the number n minus the number of predictors you have minus 1. All right, so that's the f-test, which you can do, and basically that's just going to test the null hypothesis that all of your beta coefficients are equal to 0, and the alternative is that at least one is not equal to 0. Another way to compare models is going to be r-squared. And so r-squared, it's going to have the same definition. It's still the sum of squared model divided by the sum of squared total, which we could rewrite like this: 1 minus the sum of squared errors over the sum of squared total. Why are these two things equal? Exactly, yeah, because we could rewrite this numerator as the sum of squared total plus minus the sum of squared error. And that's going to be equal to the sum of squared model. And so if we did that, then we could rearrange it to get this second part down here. And so as is, if you add a predictor, this is always going to increase regardless of how informative that predictor is. And so therefore we've got this r squared adjusted, which I think you've seen in your output. It also comes out of the summary function that basically incorporates a small penalty for adding more predictors. And so the equation for that, rather than being 1 minus sum of squared error over sum of squared total, it's 1 minus sum of squared error over n minus k minus 1 divided by sum of squared total divided by n minus 1. So how does this relate to r squared that we've seen so far?
Using n minus 1 on the denominator and then n and k minus 1.
Exactly. It's just it's basically dividing the numerator and denominator by their degrees of freedom. So it's adding these two little factors. And so the intuition behind this is if you take this sum of squared total divided by n minus 1, this denominator, this is equal to the sample variance for y. And the numerator here is equal to the mean squared error. And so r squared adjusted is just 1 minus the mean squared error over the sample variance. And so basically what's happening is the denominator is going to stay the same. This is always going to be the same regardless of what model you fit. This is just the variability of your outcome y. And the numerator here, it's going to increase when a new predictor is added to the model if the decrease in the sum of squared error is not sufficient to offset the decrease in the error degrees of freedom. So basically, if that sum of squared error is decreased by more than this n minus k minus 1 over n minus 1, then it's going to change it, and otherwise it will increase. So the r squared adjusted can actually decrease when a weak predictor is added to the model. So this makes it a little bit of a nicer metric when you're trying to compare models, because basically what you could do is you could sequentially add variables until you see the r squared adjusted decrease, and then you could stop adding variables at that point, which would basically suggest that that additional variable isn't adding kind of substantial information to your model. Okay, so in the last couple minutes, let's do one more quick application exercise. We're going to use a new data set here, this NFL 2007 standings data that comes from the Stat2 data package. And so this has the standings in 2007 for some National Football League teams. And we are going to try to predict the percent of games that were won, so this win percent, from points for, which is the total number of points that were scored by these teams. And so if you fit that model, then examine r squared and r squared adjusted. And then I want you to fit a model that, a multiple linear regression model that includes both points for and points against, and examine the r squared and r squared adjusted model, and then determine which you think is better for predicting win percent. So I'll give you a couple minutes to work on that, and then we'll do it together. right, between these two models, which had a higher R squared adjusted value? Where can you find the R squared adjusted values for these? The summary function, yes. And which model do you think is better for predicting win percent? Points for and points against, exactly. That one had a higher, both R squared, which we would expect. R squared is always going to be higher when we have more variables, but it happened to also have a higher R squared adjusted, which indicates that this is probably a better model for this. So let's do that together. So let's see. If I wanted to fit a model with, let's call this model 1. And this is going to have, what would I put it for my Y variable here? Win percent. And my X, 0.4, is this capitalized? I can't remember how that goes. Let's see, we'll see in just a second. Here we go. All right, so there's my, and if I wanted to get the R squared adjusted, what would I do to see that? Summary, exactly. All right, and what is my R squared value for this? 0.7615. And how would you interpret that, like in words? What does that mean? Yes, so 76% of the variability in win percent, so in the percent of games that are won, can be explained by the points that the team scored overall, so the points for. This, I think, makes sense. If you're scoring more points, you're probably winning more games, and so it's sort of a logical thing. Now, whether or not this is a sensible prediction model is another question, like why would it be useful to know the total points that are scored, to be able to predict the win percent by the total points that are scored. But perhaps if you had like past data and you knew in the past kind of how often people were scoring, how many points people were scoring, maybe that could help you predict how often they would win in the future. Okay, so for my model 2, I'm now going to do a multiple linear regression model. I'm going to have the same y variable, but if I wanted to adjust for both points for and points against, what would I do? Points for plus points against, and my data is still going to be this NFL 2007 standings. And so now what's my R squared here? 0.88, and what's my adjusted R squared? 0.87. And so that suggests that even after this little penalty that we've included, we still have a higher adjusted R squared. And so than we did in our model that didn't include that variable. That one only had an adjusted R squared of 0.75. So this suggests that adding this variable substantially adds to our ability to predict the win percent. All right. Are there any final questions?